Algebra 2, Chapter 9, Section 7, Probability of Multiple Events. What we're going to work on in this lesson, we're going to find the probabilities of events A and B and the probabilities of events A or B. So some things we're going to learn are dependent events, independent events, and mutually exclusive events. So let's just jump into it. When the outcome of one event affects the outcome of the second event, the two events are dependent of each other. When the outcome does not affect the outcome of the second event, they are independent events. So let's look. Classify each pair of events as dependent or independent. Roll a number cube and then toss a coin. Well, since the two events do not affect each other, they are independent. Pick a flower from a garden and then pick another flower from the same garden. Well, since picking the first flower affects the possible outcomes of picking the second flowers, they are dependent events. Okay? So, suppose you select a marble from a bag of marbles. You replace the marble and then select it again. Are your selections dependent or independent? Well, you're drawing from the same bag, but since you replaced it, the marble you took out, the probability is going to be the same. So it's an independent event. The number of marbles is the same after the marble is replaced. Next example. So probability of A and B. If A and B are independent events, then the probability of A and B is nothing more than the product of their probabilities. The probability of A times the probability of B. Okay, so I think of it this way. What's the probability of flipping a heads on a quarter? 1/2. What's the probabilities of flipping a tail? 1/2. So the probability of heads is 1/2. The probability of tails is 1/2. So what's the probability you'll flip a head and then a tails? Well, it'd be just 1/2 times 1/2, which should be 1/4. Okay, that's the way I think of it. I always put everything in terms of like quarters. All right. Suppose your favorite radio station is running a promotional campaign. Every hour, 4 hours are chosen at random to select 2 songs. You call the station once at 7 and once at 3. What's the probability you'll be selected one of the 4 callers? Well, at 7 a.m., let's look at this. Calls received are 125, and at 3 p.m., the probability, or there's 200 calls received. So what's the probability at 7? Well, how many are they choosing? They're choosing 4. And how many people call? 125. Okay, what's the probability at 3? Well, they're again choosing 4 people out of 200. So the probability that you'll be a caller both times would be the probability of 7 times the probability of 3. They're independent events. So it's going to be 4 over 125 times 4 over 200, which that reduces down to 1 over 50. All right. And 4 can simplify to 2, and 50 can be 25. So now I have 2 over 125 times 25, which would be 2 over 3125, which is 0.064%. So it's not very likely you're going to be a caller both times. Okay, so remember at 7 it was 125, and at 3 it was 200. So the probability of you being a caller both times is 2 over 3,125, or 0.064%. Now suppose the radio station changes the campaign and it chooses 5 callers. So what's the probability at 7 now? 5 over 125, which simplifies to 1 over 25. What's the probability at 3? 5 over 200, which would be 1 over 40. So the probability at 7 would be 1 over 25, and the probability at 3 would be 1 over 40. So the answer is C. What's the probability of being one of the callers both times? again, just multiply the products of the probability. So it'd be 1 over 1,000, which would be 0.1%. Answer is D. All right. Now we're going to talk about mutually exclusive events. Okay. Are these events mutually exclusive? And then we'll explain exactly what mutually exclusive means. Rolling a 2 or a 3 on a number cube. Well, since you can't roll a 2 or a 3 at the same time, they are mutually exclusive. So if they don't overlap, if they both can't happen at the same time, they are mutually exclusive. Rolling an even number or a multiple of 3. So what are the even numbers? 2, 4, and 6. What are the multiples of 3? 3 and 6. Well, since I have a 6 on both of those, they are not mutually exclusive because a 6 could happen in either one. Okay, 3A. State whether the rolling an even number and rolling a prime number on a number cube is mutually exclusive or not mutually exclusive. Okay, well, what are the even numbers on a number cube? 2, 4, 6. What are the prime numbers? Okay, 1's not prime, but 2 is, 3 is, and 5 is. Well, since 2 is on both of them, they're not mutually exclusive. So if a number occurs on both examples, they are not mutually exclusive. If they do not, if there's no overlap, they are mutually exclusive. State whether the rolling an even number on the rolling and rolling a number less than 2. Well, an even number would be 2, 4, and 6. Less than 2 is just 1. Okay, so they are mutually exclusive. They don't overlap. So let's talk about the probability of OR events. If A and B are mutually exclusive, then the probability of A or B is just the sum of their probabilities. If A and B are not mutually exclusive, then the property of A or B is the sum of their properties, the sum of their probabilities minus the overlap. Okay, many statistics or measures are based on probabilities in form of P to A or B. So let's look. College enrollment. About 53% of the U.S. college students are under the age of 25. About 21% are over 34. So under 25, 53% of our college students. 21% are older than 34. So let's look at this. Let's just figure this out real quick. So between 25 and 34 has to be the rest of the population. So let's look at that. So between 25 and 34, well, it has to be 100%. So 53 plus 21 is what? 74. So 100 minus 74 is 26. So 26% of the population falls between 25 and 34. Okay. What's the probability that a U.S. college student chosen at random is under 25 or over 34? Well, the probability of under 25 is 53. And the probability of over 34 is 21. So you add those together, 0.53 plus 0.21, you get 0.74. So my answer is 74%. Okay, based on the data we just came up with, a U.S. college student is chosen at random. Find the probability the student is between the ages of 25 and 34. Well, we already figured that one out. That's 26%. Okay. A U.S. college student is chosen at random. Find the probability he's between 25 and 34 or over 34. So that would be 0.26 plus 0.21, which would be 0.47. So 47%. Find the probability they're under the age of 34. Well, there's 100% chance that they exist, and subtract 21%. So I would get 79%. Hopefully that makes sense to you. Pretty easy. Okay, let's look at the probability of events. Suppose you reach into a fruit bowl at the left and select a piece of fruit at random. What's the probability the piece of fruit is an apple or green? Well, let's count the apples. 1, 2, 3. So I have 3 apples. Oh, I lied. 5 apples out of 9 fruits. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 5 apples, and I have 3 green events. Okay, well, how many green apples do I have? So I have 5 apples, 5 over 9, 3 green items, 3 over 9, and 2 green apples, so minus 2 over 9. So you add those together. 5 plus 3 is 8, minus 2 is 6, 6 over 9, which would simplify to 2 over 3. Now that's the book way. What I'm going to do is this. I'm going to count green and apples. So there's 1, there's 2, there's 3, there's 4 in the middle, there's 5, and there's 6. Same way. If it's a small sample size, you can just do it by hand. Find the probability of an apple or red. Well, everything red in there is an apple. So we're going to write 3 over 9. That's the red stuff. Plus, well, the rest of the apples is 2 over 9. So the probability of being red or an apple is just 5 over 9. Find the probability of it being green or a citrus fruit. All right, so I see what looks like to me an orange, and a lemon. So I see 3 citrus fruits, so 3 over 9. And what's green? 1, 2, 3. So I see 3. So that's 6 over 9, which would be 2 over 3. So the answer is B, 2 over 3. Okay, hopefully that makes sense to you for probability.